Okay, hello Precalc C, this is Tuesday afternoon. Over the weekend, you were supposed to watch a video concluding our review of the unit from last year on 3D vectors, equations of planes, cross products, vector equations of lines, and stuff like that. And then you had to do some homework. Some of it was pretty easy, but I think the last three problems were pretty hard. And I did not get to these problems at all on Tuesday in period 6 in the morning. I probably won't get to them today in periods 3 and 4 either. So I'm recording this video just before class, and I'll post it this afternoon. Here we go. I'm just going to do these three problems. They take maybe 10 minutes each. So number 13 from page 877 says, the exact words are, find the point of intersection of the lines and the angle between the lines. Okay, find the point of intersection of the lines and the angle between the lines. Alright, so here we have two lines. This is not actually the form that I use when I am finding the, when I'm talking about the equation of a line. So let me translate this into just maybe some more comfortable notation, which I think I did on the worksheet. If we call this line L and we call this line M, then really what we're saying here is that line L should be written as x, y, z equals, so t is the parameter here, so that's 6, negative 5, 1 plus t times the vector 1, negative 2, 3. Okay, so I'm just that's exactly how you are supposed to interpret. This was referred to as a line, or these were referred to as two lines, and the understanding is that this is just kind of a different way, a different formatted way of talking about the vector equation of a line. We've done it in the past, I think with Mr. Kirk, you guys did it more like this. That's how I did it in the review. Okay, and then if I'm calling this line M, then I can also refer to line M, a line in 3 dimensions, using the vector equation of a line. Every single arbitrary point on that line has the property that you go to the point 7, 5, 8, 7, 5, negative 8, 7, 5, negative 8, and then you follow some unknown number of times the vector 5, 2, 3. Okay. The vector 5, 2, 3 is the direction that that line is pointing in. Going in the direction 5, 2, 3 sends you to all the sort of points on that line, and I should use a new letter, which the book also does. They switch to the letter S, so T is some real number, S is some real number. Okay, and if you're still struggling with this a little bit, I mean, you probably aren't, but 5, 2, 3, right? So the idea is like if I set S equal to 0, then I'm at the point 7, 5, negative 8. But when I set S equal to 1, well, now I'm at the point 12, 7, negative 5. If I set S equal to 2, so if you think of S as like seconds or something like that, if you think of it in terms of time, every second that goes by, my vector, my point on line M is going to be increasing by 5 in the x direction, 2 in the y direction, and 3 in the z direction. Okay, good. So now we have these two lines. Well, what's the actual task? We need to find the point of intersection of these lines. Okay, this problem is actually a little bit easier than it could have been, because here we're just being told to find the point of intersection, which is to say we're told that these lines intersect. But it is not obvious at all that these lines intersect, and a slightly harder question would be, do these lines even intersect? So let's pretend to answer that question. Do these lines intersect? And if so, find the point of intersection, and if they don't intersect, then show that they don't. Alright, well, okay. How am I going to see if these two lines intersect? Well, one thing I could do is to, so here's the way. There are basically two ways to do this. do not have the meter sticks, so I'm going to use these things. Yeah. Okay, so I have these sort of two lines in 3D. And, well, in general, there's nothing that means that these lines need to intersect at all. So how can I see if they do? Well, one thing I could do, and this works almost all the time, is to sort of crawl above the lines, so to speak, and look kind of down on them. If you look down on the lines, then they appear to intersect, sort of without depth perception, so to speak. In other words, if you ignore the z-coordinate, these lines are almost definitely going to intersect. The only time they wouldn't is if the lines were sort of parallel to each other, essentially. But probably, really this question, and okay, if the two lines were parallel to each other, you could tell because they would have the same direction vector. These two direction vectors are not the same, so these two lines are not parallel. And since these two lines are not parallel, they either intersect or they're skew, which is kind of what I was indicating first. So we need to narrow it down to, are these lines skew or are they intersecting? Well, what we're going to do is sort of project the lines down onto the ground, which is another way of saying we're going to ignore the z-coordinate temporarily, and we're just going to find where the x and y coordinates are the same. And once we find where these two lines have the same x and y coordinate, we can simply check to see what the z-coordinate is. And if it turns out that the z-coordinate is also the same at the point when they have the same x and y coordinates, then there is a point on both lines with the same x, y, and z coordinate. And if where the x and y coordinates are the same, the z coordinate is not the same, then it means that the lines are kind of above each other, and in fact then they must be skewed. Okay, so this is probably how you did this problem last year, if you did this problem. So here we have now, we are sort of in option 1. And option 1 says, let's ignore the z coordinate and let's just look at the x and y coordinates. In other words, I want to see for what values of s and t are the x coordinates the same. So when does 6 plus t equal 7 plus 5s? In other words, when do these two lines have the same x coordinate, and when do they have the same y coordinate? So that's negative 5 minus 2t equals 5 plus 2s. Okay, well, now I have just a system of equations, and I can just solve this system of equations. So, okay, let's do it maybe the kind of casual way, I guess. We can do that. So, just in a sort of doing a more kind of chill Algebra 1 type thing, what do we get? We get 5, I'll do it like this, negative t plus, sorry, no, I'll just be normal. T minus 5s equals 1, and over here we have negative 2t minus 2s equals 10. I think I did that right? Yeah. Okay, and so I said I would do this the casual way, so I'll multiply both sides of this by 2, so that gives me 2t minus 10s equals 2, and negative 2t minus 2s equals 10. And now if I just add these two equations, I'm just going to get negative 12, hope I'm doing this right, yeah, well, I guess if I made it this far, I might as well not be casual. Let's just keep on going. Okay, so if I add these two equations, what am I going to get? Down here, let me replace equation 2 with the sum of it and equation 1. What does that give me? It gives me negative 12s equals 12. And the first equation I can now divide by 2 back again. So I get t back to t minus 5s equals 1. And okay, I'm kind of just done now because I see that s has to be negative 1. And so if t minus 5s equals 1 and s is negative 1, let me just plug in a negative 1 for s. And if I do that, I get that that's negative 5, so, or that's 5 rather, so I subtract, so okay. So I get t equals negative 4, s equals negative 1. Alright, this was sort of just a long way, maybe too long, to solve this system of equations. And so I'll put this here. And what have we accomplished? What we've accomplished is I have now found the value for s and t. T is negative 4 and s is negative 1. What was I trying to do again? I was trying to find the places on these two lines where their x-coordinates and y-coordinates are the same. And now I just go back here and look back at the lines again. So take line L, for example. Well, on line L, when t is negative 4, where am I? Alright, well, when t is negative 4, then the x-coordinate is 2. The y-coordinate is 8 minus 5 is 3. And the z-coordinate, when t is negative 4, is 1 and negative 12, so that's negative 11. Okay, good. So, okay. Now, what about the value when s is negative 1? Well, when s is negative 1, I get that the x-coordinate is 2. The y-coordinate is 3. Okay, I expected that to happen because the very solution of this system was to find the ordered pair s and t such that these two lines have the same x and y coordinate. And sure enough, what is the, when I plug negative 1 in for s in the z equation, I get negative 11. And so it turns out that these two lines do intersect. Okay, I knew that already because the book told me that these lines intersect, but now I have found the point of intersection. They intersect at 2, 3, and negative 11. Okay, and if I had gotten different values for z, then I would know that where the lines have the same x and y coordinate, their z coordinates are different, and thus there can't be any point where the x, y, and z's are the same. Alright, there's another way to do this problem, and the other way is, it's very, very similar actually. It's almost the exact same thing. There's just kind of like a minor difference in how you think about what you're doing. And the minor difference is that instead of all this kind of geometry and stuff, you just go right for the system of equations. Here is the one line, here's the other. The question is, do these lines ever meet? Well, if you want to know whether these lines ever meet, let's pretend for the moment that we still don't know, then you're really just asking the question, hey, is there a t and an s such that the x's, the y's, and the z's are all the same? Okay, well, for this, then, I can just put all three of these into a system of equations. So I get 6 plus t equals 7 plus 5s, negative 5 minus 2t equals 5 plus 2s, and 1 plus 3t equals negative 8 plus 3s. Alright, and now, never mind kind of all this geometry stuff, the question of whether these two lines intersect is now just completely contained within this system. If I can find a value of s and t for which this system has a solution, in other words, all three of these equations are true, then the lines intersect. And if this system has no solutions, then there's just no sort of time on this line and time on this line for which we're at the same x, y, and z coordinate. Okay, this is kind of nice because we have been solving systems of equations, and we actually have some vocabulary to describe this. This is a system of 3 equations in 2 variables, so this is an overdetermined system of equations. And we should, this is the kind of thing you sort of never do in Algebra 1, but here is a reasonable time when you might want to do that. So this is a sort of a basic kind of geometry question whose solution can be found by solving this overdetermined system. Okay, now let's just do it. I probably don't have space, so I'm probably going to erase my option 1, and actually a lot of what I'm about to do now is kind of algebraically repetitive. Okay, too bad, or something. So let's now let's go sort of carefully doing stuff to this system. Well, maybe the first thing I'll do is kind of clean it up a little bit, and so we get, well, what do we get? T minus 5s equals 1, just like before. Negative 2t minus 2s equals 10. And now 3t minus 3s equals negative 9. Okay, as it turns out, I can simplify both lines 2 and line 3. So if I do that, I get t minus 5s equals 1. Here I will divide by negative 2. And if I divide by negative 2, I get t plus s equals 5. Yeah. And, yeah. If I divide negative 5, sorry. And if I divide here by 3, I get t minus s equals negative 3. Okay, good. Well, now I have just this system of 3 equations and 2 variables. Let's proceed. Just double check myself. Yeah. Okay. So what should I do next? Well, you've all now gotten kind of used to this. I'm going to use this 1 to kill all the things underneath it. In other words, I'm going to use Gaussian elimination. So I'm going to replace row 2 with negative row 1 plus row 2. And I'm going to replace row 3 also with negative 1 plus row 3. And so what I get is t minus 5s equals 1. Here I get 7s equals 6s. Oh man. 5 and 1 is 6. And equals negative 6. And here I get 6s equals, sorry, what am I doing? Negative 5 and negative, no, I get 4s equals negative 4. Okay, good. That's kind of what I hoped would happen, because now, what have I just revealed? I've revealed that this is t minus 5s equals 1, and when I divide this by 6, I get s equals negative 1, but here I just also get s equals negative 1. Okay, and don't be confused by that. If you want to be extremely weird about this, or you know, kind of solving this problem like a math teacher would, you would then sort of like, you know, it's clear that this third equation is just totally redundant, but if you really want to, you could always, you know, replace equation 3 with like negative row 2 plus row 3, which is another just way of saying, you know, subtract the 2 equations, and then you just get 0 equals 0, sort of convincing yourself that that third equation is just really not needed anymore. Let's multiply row 2 by 5. So if I multiply row 2 by 5, then I get 5s equals negative 5. And now I can finish this problem off by adding these 2 equations. So I will replace row 1 with row 1 plus row 2. And when I replace row 1 with row 1 plus row 2, I get t equals negative 4. That's the answer, right? Yeah. T equals negative 4, and s equals -1. I'll put this row 2 back again. Okay, so in all the sort of tedious detail, I have just solved this system of equations using Gaussian elimination, and but this time, because I was so disciplined in my approach and replaced every system with an equivalent system as I was going, what that means is that this system just does have a solution. It has a solution that t equals -4 and s equals -1. So now, I don't even really, if my only goal were to determine whether or not these lines intersect or not, I could stop now and say, yeah, these lines do intersect. Never mind finding what the point of intersection is, I know that, that the lines intersect because, well, when t is -4 and s is -1, that's a solution to this original system, and this original system is asking, are the x, y, and z coordinates ever the same? Alright, I like option 2 because if I don't know whether the lines intersect or not, it gives me a clear explanation of why, but also I think this is a nice skill to have. Okay, the part 2 of the problem, I'm going very slowly here, I'm sorry. The part 2 of this problem, it says to find the angle between the lines. Well, now that I know that these lines meet, finding the angle between the lines is supposed to be is a question that sort of makes sense. And okay, if these are my 2 lines and they meet somewhere, then well, these lines are pointing in a certain direction. So the question of what is the angle between these lines just reduces to the question, what is the angle formed between the direction vectors of these lines? And so what I really need to do to do this part 2 is to just find the angle formed by, let's just temporarily call it u, that is the vector 1, -2, 3, and the 1, -2, 3, and the vector v, which is 5, 2, 3. And if I can do that, then I will be done. Well, I know how to do this because u dot v is mag u mag v cosine theta. And therefore, if I want to find the angle between any 2 vectors, the cosine is just going to be the dot product divided by the magnitudes. Let's see if I can do this in my head. The dot product here is going to be 5 minus 4 is 1, and 9 is 10. And the magnitude is going to be, oh boy, 9 and 4 and 1, so that's 14. So root 14, and 25 and 4 is 29, and 9 is 38. And I guess I could pull a root 2 out of both of those, so that becomes like 5 over root 7, root 19. Alright, and now I'm just going to stop, because I don't have like a calculator or anything, but basically the answer to this problem is that the angle between these 2 lines is just the arc cosine of 5 over root 7, root 19. I hope I didn't make any mistakes there. Okay, that's 1 down, 2 to go. I think I'm out of time, so I'll pause this now. Okay, we're back. Here we go. Let's do number 25 from this same page. 25 says, find an equation of the plane passing through the 3 points. Okay, so you're given these 3 points. They are 4, -1, 3. Let's call that point A. 2, 5, 1. Let's call that point B. And -1, 2, 1. Let's call that point C. Okay, so, yeah. What should we do? We need to find the equation of the plane that goes through all 3 of those points. Let's do it. All right. Well, I think this is one is pretty easy. I mentioned this on the video. This is something I think you did do this last year, but okay, we can go over it. So it goes like this. You take your 3D coordinate system, and you have some kind of plane. Never mind drawing the plane accurately or whatever. This plane is kind of floating here in 3 space, and there's only one thing I know about this plane, is that it goes through these 3 points. So let's put A here, B here, it doesn't matter, and C here. Okay, and I guess I can just add the coordinates to these. This is 4, -1, 3. This is 2, 5, 1. And C is -1, 2, 1. Alright, so I need to find the equation of this plane. Well, as we reviewed in the video over the weekend, to find the equation of a plane, it suffices to know the normal vector to that plane and a point on that plane. And so I need to find a normal vector that's sort of coming out of this plane at a right angle. Well, and there's one sort of obvious way to do this. I have these points, and if I connect them, if I connect B to A and B to C, it doesn't matter which ones you use, you will get these vectors, this vector BA and this vector BC. And since A and B are in the plane, vector BA will lie in the plane. And since B and C are in the plane, vector BC will lie in this plane. And if I take the cross product now of these two vectors, then I will get this normal vector, and this normal vector will be perpendicular to BA and also perpendicular to BC. And if it's perpendicular to BA and also to BC, then it must be perpendicular to the plane, and therefore that's the normal vector. So actually that's really just it. I'm gonna, so I find out, well, okay, what are you, vector BA? From B to A, I go, x increases by 2, y goes down 6, and z goes up 2. So that's vector BA, and vector BC is -3, I'm just doing this in my head, -3 and 0. See if I did that right. Yeah, -3, -3, 0. Is that really true that they have the same? Yeah. Okay, good. Well, now I just need to take the cross product of these two. So, well, what is 2, -6, 2 cross? Well, okay, here I'm sort of tempted to, well, I guess I'll just leave it. -3, -3, 0. So I don't really need to take the cross product of BC. I just need to take the cross product of of any vector which is parallel with BC. So if you want to make all these numbers easier, instead of actually doing BA cross BC, you could just divide this vector through by 2. So now it's just kind of a smaller vector, but it's still pointing in the exact same direction. And this vector, -3, -3, 0, I could just replace it with the vector just 1, 1, 0. In other words, just divide it through by -3, and now that's a vector that's pointing still in the same direction. And if you take the cross product of two vectors which are pointing in the same direction that BA and BC are pointing, you're still going to get a normal vector. There's not just one answer, because there's an infinite number of vectors which are normal. Alright, this is just going to make the problem a little bit easier. So how do you do this? The way that you learned to do this last year, and also we reviewed it, is this. And then you kind of do this thing. So alright, what do we get? We get I times, you mentally delete the row in the column, -3 times, maybe I should just do this out properly. So you get this little thing, minus j times 1, 1, 1, 0, like that. And plus k times 1, -3, 1, 1. Okay, and then we just do this. What do we get here? We get -1, because 0 minus 1, minus j times, this is also -1, 0 minus 1, and this is 1, minus 3, so that's, no, 1 minus negative 3, so that's just positive 4. Right? 1 minus negative positive 4. Yep. So I think I got negative 1, 1, 4. Sort of like not really confident of myself. No, that's right. Negative 1, 1, 4. Now, if you used, if you chose a sort of a different point to be your anchor point, if you had A here, or C here, or you did them in different directions, or you didn't divide first, you may have gotten a different normal vector. But there's probably like 20 different ways to do this. But no matter if you did it correctly, the normal vector you get should be parallel to this one, and that's all that matters. All right. So here we go. Once I know that my normal vector is negative 1, 1, 4, or at least that's what I got the way I did it, then I'm prepared to write the equation of the plane because I know from what you learned last year and what we reviewed that the normal vector to any plane is that these components are the coefficients of x, y, and z in the equation of the plane. And so we get negative x plus y plus 4z, and the only thing I don't know yet is what the constant is. And in order to find d, I can just plug in one of these numbers. I'll plug in c. So if I plug in c, I get negative 1. Yeah, and so it turns out that d is 7, or no, rather 7 plus d is 0, so d is negative 7. And therefore, my final answer is negative x plus y plus 4z minus 7 equals 0. And that is my final answer. Of course, you could multiply through by negative 1. That would also be a correct answer, which is kind of what I got on my paper. Or you could divide through, but anyway, there you go. Okay, one more to go, number 33. And this is actually pretty interesting. So I will send this one for everyone to listen to. This is, I think, the hardest thing from the 3D vectors unit that I'm asking you to do. This is something that I think Mr. Kirk gets to some years, but last year he didn't get to it, and I taught it to you via video. So this was your chance to practice it. It's number 33, and number 33 gives you 2 planes and asks you to find the equations of those 2 planes. Okay, so we get x plus 2y plus 2z equals 4. And here we have x plus x plus y plus 2z equals 4, and x minus 2y plus z equals 10. Okay, so those are my 2 planes. And right, how should you do this problem? Well, the way I taught you to do this in the video from last weekend, I'm going to call this the Pre-Calc B method. The Pre-Calc B method that you're supposed to learn in Pre-Calc B is to do what I kind of told you to do already. This is the sort of the geometric method. So you have these 2 planes. Perhaps it's worth it to name them, like, P and Q, okay? So this first plane is P, the second plane is Q. And we're going to think about this geometrically. Okay, I don't really feel like getting all those folders and stuff out again, but maybe I have to. So, yeah. Man, sure. So, yeah, there's this sort of idea here that I have these 2 planes, and I want to find this line, which is the line of intersection of those 2. Let's do this again. Yeah. So I want to find the equation of this line, which is the line of intersection of these 2 planes, the line where the 2 Yeah, where the two planes meet. And how do I do this? The way you do this is by taking the cross product of the normal vectors. Plane P has this vector 1, 1, 2 is the normal vector, and plane Q has normal vector 1, negative 2, 1. And these vectors are sort of pointing out of the plane. I definitely can't do this, but I will try. Once again, it was sort of a failure last time too, but well, put this away and just say, okay, take these two vectors, which are normals. Can't believe I'm doing this. Take these two vectors, which are normal to the two planes, and those two vectors, those two normals, if you take their cross product, then you get a vector which is going to be perpendicular to both of them. But if you're perpendicular to both of these vectors, then you are just actually parallel to the line of intersection. So the direction of the line of intersection is just the is pointing in the same direction, or it just is the same as this vector that we get by taking this cross product. Okay, hopefully that's kind of clear. Let's do it again. So I get this ijk 1, 1, 2. And okay, I want to kind of do this maybe a little bit fast this time. I'm going to do this in my head. Let's see if I don't. Let's see if I make a mistake or not. So I get 1 minus negative 4. That's 5. And here I'm going to get shoop shoop, and then that's going to be 1 minus 2. So that's negative 1. And for k, I get shoop shoop, negative 2 minus 1. So that's negative 3. Okay, so let me double check my work because I do sort of doubt myself. Here I got 5, 1, negative 3, and according to my paper, that's right. Okay, good. So by taking the cross product of the normal vectors to these planes, I get a vector which is pointing in the right direction. And now it becomes just a matter of finding a point which is on both of these planes. And what is a point which is on both of these planes? Well, now is where we sort of just set z equal to 0. If I need a point that's on this plane and a point that's on this plane, that just means a point on the line, of course. And there are an infinite number of these points on the line. So I have a lot of different points to choose from. There's not just one answer to this. So if there's not just one answer, let me simplify my life and make my numbers as small as possible by just letting z be 0. If I let z be 0 in this first equation, then I get x plus y equals 4. In other words, I'm restricting my attention to points on this plane which have a z coordinate of 0. And if I set z equal to 0 in the second equation, then I get x minus 2y equals 10. And therefore, I'm setting my, I'm focusing my attention on points which are on plane Q, but also the z coordinate is 0. And if both of these are true, and I think I can solve this problem by just subtracting these two equations. If I subtract these two equations, I get negative 3y equals negative 6. And so y is 2. And if y is 2, then x has to be 2 also. If I subtract these two equations, 1 minus negative 3, that's positive 3. Made a mistake there. So y is negative 2. And if y is negative 2, then x is 6. Okay, what have I just learned? What I've just learned is that the point 6, negative 2, comma 0 is on plane P and also on plane Q. And therefore, I'm done. I can now, I'm just going to squeeze it up here, the vector equation of this line now is x, y, z equals, I need a point that's on that line, well I just found one, it's 6, -2, 0, and I need a to know the direction that the line of intersection is pointing in, and it's this one right here. So T 5, 1, 3, and 5, 1, -3. Cha cha. Okay, so letting T be sort of all possible real numbers, I ride along this vector in this direction, starting at this vector, and that gives me every single point on this line. Okay, that is one way to do it. It's the way that our book, if you read the book, teaches you how to do it. It's the way that I taught you how to do it in the video I made over the weekend. It uses Pre-Calc B knowledge only. But, and this part might kind of blow your mind or something, or it should arguably blow your mind. There's an entire other perspective. So now I'm going to redo this entire problem. I'm going to redo this entire problem from a totally different perspective, from the Precalc C perspective. After all, we are in the middle of a unit on solving systems of equations. And so, though I pursued a sort of a geometric approach over here on the left, I could also pursue an algebraic approach. And I think seeing these two different approaches will lead to some sort of deep understanding. You can get a lot out of doing this sort of same problem in two different ways. You see connections and things. So what's the Precalc C method? Well, if you give me these two planes, and you say find the equation of the line of intersection, well, yeah, okay, this is a plane, but really this is just a line of algebra, or an equation of algebra. This is also an equation of equation of algebra. And so if you're asking me for the intersection of these two planes, you might just as well be asking me, okay, well, give me all the points which are on this plane and also on this plane. We know that that collection of points will form a line, but really that's all this is saying. Give me all the points that are in this plane and also all the points that are on this plane. In other words, give me all the points which satisfy this equation and also satisfy this equation. Well, if you phrase it like that, now it just sounds like a system of equations. And in fact, it is. If you give me x plus y plus 2z equals 4, and x minus 2y plus z equals 10, and you just say solve that system, well, the solution to this system of equations is going to be all the points which satisfy both equations. That will be all the points that are on both of these planes. That will be the line of intersection. So the Precalc C method is to ignore all this cross product stuff and vectors and all this kind of junk and just treat this problem for what it is, which is a system of equations. In fact, it's a system of two equations in 3 variables. So this is an underdetermined system of equations. And now we're just going to solve it. Okay, now I taught you Precalc C. I taught you Gaussian elimination, just like an hour ago. So you wouldn't have known that at the time that you did this homework, but you do now. You know Gaussian elimination, and so the strategy here is, dude, just use Gaussian elimination. So we do it. What is the Gaussian elimination algorithm? It says make that a 1, and then get rid of that by clearing some space. Well, okay, let's clear some space. And if I do that, am I doing this right? Sure I am. If I do that, I will replace row 2 with negative row 1 plus row 2, cha. So I get x plus y plus 2z equals 4, and jump. And here I get negative 3y and negative z and negative 4. Okay, and no, sorry. Negative 4 and 6. Negative 4 and 10 is 6. Okay, so in only one step, I am kind of done because I have already achieved my triangle formation, and there's actually just nowhere left to go, right? There's no other equations, so I sort of can't do anything else. And so the Gaussian elimination just stops. There is one more thing to do, and it seems sort of like maybe a waste of time, but I promise you it isn't, and that is to to divide through here by -3, it just kind of makes everything a little bit easier. I mentioned this in class. If we sort of keep going until that leading coefficient is 1. So okay, I'll do that. There's even something else. Well, I'll stop there. So x plus y plus 2z equals 4. And here I get y plus a third z equals -2. Should we just double check that? Divide by -3, divide by -3, divide by 2. Yeah. Okay, so there it is. But you might be sort of wondering, well, dude, what do we do now? Don't fear, because this is the thing that we did in class today, or yesterday, which is, yeah, there are an infinite number of solutions. Of course there are an infinite number of solutions because there are only two equations. How do we write that infinite number of solutions? Well, you introduce a free parameter. So you say, okay, let z be represented by free parameter a. If z is a, then what's y? Well, y is negative a third a minus 2, if you see what I'm doing there. And what's x? Well, this is one's going to be a little bit harder, but x is going to be, well, it's going to be negative y, negative 2z plus 4. In other words, x is going to be the opposite of negative 1/3 a minus 2 minus 2a plus 4. And hopefully you see what I'm doing. I'm arbitrarily assigning a free variable to the sort of a free parameter, as they call it, to this variable z. I'm expressing y in terms of z by adding 1/3 z to both sides here, and then I'm expressing x in terms of both y and z. So what do I end up with? 1/3 a plus 2 minus 2a plus 4. So this whole thing becomes negative 5/3 a plus 6. Okay, and I will now stop and say that this is my final answer, seemingly, to this problem is, well, it's negative 5/3 a plus 6, comma, negative 1/3 a plus minus 2, comma a. And it's perfectly respectable to just stop there and to say, okay, the solution to this system of equations is all of the ordered triples of the form negative 5/3 a plus 6, negative 1/3 a minus 2a. Okay, but there's a kind of a key connection left to make. What relationship does that have with what we did over here, where we took the cross product and found a point on both equations? Well, okay, unfortunately I have to erase this because I'm running out of space, but now, and then we'll sort of be done here, is you can take this and rewrite it slightly. Let's rewrite it slightly by sort of splitting it up into the parts that have a and the parts that don't. In other words, let's write this as 6, negative 2, 0, whoa, plus negative 5/3 a, comma, negative 1/3 a, comma, a. So all I did was to kind of basically like decompose this ordered triple into pieces that have a's in it and pieces that don't. Whoa! And now you can factor out this a, and what we have now is something which looks almost identical to what we had up here when we did it the old way, right? What this might as well be saying is, yo, the equation of the vector equation of this line is going to be 6, negative 2, 0 plus a times negative 5/3 negative 1/3, 1. And of course, whether you use A or T, who cares? It doesn't matter. It's the same idea. It's just a parameter ranging over all real numbers. And of course, this vector and this vector are just the same thing. If you just divide this through by -3, I guess, then you get this one. So they're of course scalar multiples of each other, and so both of them are completely legitimate answers. Okay, and so here you see that there are these two totally different ways to find the line of intersection of two planes, sort of geometrically with vectors and cross products, or purely algebraically by just doing Gaussian elimination directly on the two equations. Introducing a free parameter to write your solution as a set of ordered triples, and then potentially you could even just stop here with what's in the red box. But I wanted you to appreciate that this thing here in the red box, sort of in disguise, is actually just the vector equation of a line. And with kind of one or two more steps of work, or really you could just do this all in one step once you've seen it coming, this thing here in the red box can be rewritten in what you consider to be the more standard format for the vector equation of a line. Okay, so that's two different ways to do that problem. Good, I will post this video right now. Okay, bye.